Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood the formal definition of TOC. Along with that, we also saw that theory of computation is the field of study that stands on three pillars: computability theory, complexity theory, and automata theory. This is the second lecture of the course, that is computability, complexity, and automata theory. So we will discuss each of these pillars of theory of computation one by one in this lecture. So basically we have only one topic to cover today, that is pillars of TOC. So let's get started. Let's start with the very first pillar of TOC, that is computability theory. Computability theory studies which problems are computable and which are not. Now, what is the meaning of the word computable? Computable means solvable, the problems that can be solved by computers. So, computability theory tells us that which problems are solvable by computers and which problems are not solvable by computers. So, let's understand it with an example. Here we have 5 numbers: 4, 0, 3, 1 and 2. And you want your computer to arrange these 5 numbers in ascending order. Now, do you think your computer will be able to solve this problem? Yes, of course. Sorting the numbers in ascending or descending order is a very simple problem for a computer. Computer will just keep 0 here, then 1, then 2, then 3, then 4, and we will get the result like this. That means this is a very easy problem for a computer, and that is why it is called a solvable or computable problem. On the other hand, let's take a different example. Suppose this is you, and you are very happy today. Now you want your computer to tell you that what will be your mood tomorrow, happy or sad. Now this is highly uncertain for a computer to tell you whether your mood will be happy or sad tomorrow based on your today's mood. That is why this problem is an example of unsolvable problem or a non-computable problem. In this way, we have understood that sorting the numbers in ascending order is a computable or a solvable problem, while mood prediction is an example of unsolvable or non-computable problem. By this, we are done with computability theory. Let's discuss the second pillar of TOC, that is complexity theory. Complexity theory deals with determining whether problems are efficiently solvable, which means that complexity theory tells us that which problems are efficiently solvable and which problems are not efficiently solvable. That means the agenda of complexity theory is not to determine whether a problem can be solved or not, because that's what we discuss in computability theory. In complexity theory, we determine whether a problem can be solved efficiently or not efficiently. Now, what do you mean by efficiently solvable? It means how longer does it take by a computer or a machine to solve that particular problem? Few seconds, few years, or even greater than the age of universe. So let's understand complexity theory with the help of an example. Again, we have 5 numbers: 7, 4, 6, 3, and 8. And you want your computer to select only the even numbers out of these 5 numbers. Now, what do you think? Can your computer solve this problem? Of course, selecting the even numbers out of the given set of numbers is a very simple problem for a computer. You all have written the code for checking whether the given number is even or odd. But, as I have told you, in complexity theory, we are not interested in determining whether your computer can solve the problem or not. We are interested in knowing, can your computer solve this problem efficiently or not? So let's check it out. Computer will take 7, divided by 2, remainder will be 1. That means 7 is an odd number. And when computer takes 4 and divide it by 2, it will have 0 as the remainder. That means 4 is an even number. In this way, computer will be very easily able to tell you that only 4, 6 and 8 are the even numbers. That means this problem is very efficiently solvable by computers. Now on the other hand, let's take a different example. This is a 39-digit long number and you want your computer to check whether this number is a prime number or not. Now what do you think? Can this problem be solved by a computer? Yes, of course. But as I said, we want to determine the efficiency of this problem rather than the solvability of this problem. Now, do you think checking this big number, prime or not, is as efficiently solvable as this problem of selecting an even number? Of course not. This will definitely take more amount of time as compared to this problem. That means this is a non-efficiently solvable problem. And that is why checking the primality of such a big number is an example of non-efficiently solvable problem. So in the complexity theory, we have understood that selecting an even number is a computationally easy problem, while checking the primality of such a large number is a computationally hard problem. So by this, we have understood the complexity theory. And let's move to our third and last pillar of TOC, automata theory. Automata theory deals with designing abstract machines or automaton to solve computational problems. So what does it mean? It means that in automata theory, we design abstract machines or automaton to solve computational problems. Now, first of all, what is this abstract machine? Moreover, what is the meaning of the word abstract? In general English, abstract means something which is not real. So abstract machines are those machines that are not real. You cannot compare abstract machines with your washing machine or your vending machine, computer, robot, because these are real machines. An abstract machine is just an ideation. You can draw abstract machine in your mind or on paper. It is basically a diagrammatic or a mathematical representation of solving a computational problem using a step-by-step approach. So that is what an abstract machine or an automaton is. Now, what is a computational problem? Any problem that can be solved using a step-by-step approach. That particular problem is called as computational problem. So in automata theory, to solve a computational problem, we design abstract machines or automaton. Now let's understand this theory with the help of a wonderful scenario. Suppose you have a very difficult exam after 3 days. And to concentrate on your studies, you have deactivated your social media accounts, like Instagram. Now after 3 days, your exams went very well. Now you again want to come back to your normal life, so you again want to activate your Instagram account. Now while activating your Instagram account again, you may encounter with such type of page, which is a login page. Now in this page, you will first enter your username or your email ID, then you have to enter your password, and when you click the login button, you will get access to your account. Now, why I have discussed this scenario with you? This is because this login system can be realized as a computational problem. I have explained you that a computational problem is a problem that can be solved using a step-by-step approach. And that's what we are doing in this login page also. Step number 1, you will enter your username or email ID. Step number 2, you will enter your password. Step number 3, you will click this login button. And finally, you will get access to your account. So this problem is an example of computational problem. And in the automata theory, we have discussed that to solve a computational problem, we design an abstract machine or automaton. So we are going to see how for this problem an abstract machine can be designed. So this is the abstract machine for a login system. So let's understand this abstract machine quickly. These three are the three states of the login system or the abstract machine. State number 1, enter ID. State number 2, enter password. And state number 3, access granted. In the first state, login system is asking user his ID. So when the user enters his correct ID, he will reach the second state, that is, enter password. Now login system is asking user to enter his password. Now here, user will either enter a correct password or a wrong password. If user enters the correct password, he will reach the final state, that is, access granted. There, user will have the access to his Instagram account. And when user enters the wrong password, he will remain at the same state. In this way, we have understood how a login system, that is a computational problem, can be represented using this abstract machine or an automaton. Now I hope automata theory is very much clear to you. In this way, we have completed our third pillar, that is automata theory. Now here, I want to tell you one important thing, that automata theory is the most important pillar of theory of computation. Why? Because automata theory constitute the major part of theory of computation. More than half of TOC is made up of automata theory. And this is the reason that in some colleges and universities, the subject theory of computation is known by its alternative names like automata theory, theory of automata, and formal languages. But you know that TOC is not just automata theory. TOC has three pillars: computability, complexity, and automata theory. In this way, we have completed our topic, pillars of TOC. So this was all from my side for this lecture. I hope your concepts are crystal clear. Thank you, and I'll see you in the next lecture.